All right, so in 2.1, we went more in depth on quadratics. We talked about what to do if it's already in the graph, if it is in standard form like this one, and then we talked about how to approach it in 2 different ways if it wasn't in standard form, it's in quadratic, which is the next slide on this. So the first one, hopefully we're getting pretty good at this, right? Vertex would be what? 4, 5. So I already know 4, 5. Here's my vertex. I know this points in which direction? Up or down? Up, right? And I know it's not narrow or wide. So I can already kind of get a visualization of what it should look like. Then it asked me to find the intercepts. So I would plug in 0 for y to find the x-intercepts. I subtract the 5, and then what happens when you go to square root that negative number? It's imaginary, which means there's no x-intercepts, which makes sense because we said this is going to point up, right? So it should make sense that it never crosses the x-axis. And then the y-intercepts, I'm going to change that f of x to y and plug in 0. Negative 4 squared would be 16. 16 plus 5 is 21. So I get 0, 21. So way up here somewhere. Okay. I still need some additional information before I can graph this. So you need at least 1 point to the left and 1 point to the right. Make it easy on yourself. So if I pick the next one, the next x after the vertex, I could plug in 5. So I get 5 minus 4 squared plus 5, 1 squared plus 5, which is 6. And I put my point there. I can use the 21, but if you didn't want to graph the 21, you could have also plugged in to the left of your vertex, which would have been 3. If I plug in 3 minus 4 squared plus 5, negative 1 squared is 1, plus 5 is 6. And I have my other point there, which should mirror the one to the right. And then I just got to connect them to make my parabola. Is there a max or a min on this function? There's a minimum, okay? And what's the minimum value? Remember, with absolute mins, we're just giving the k, which is what? 5, good. What's the domain on this function? All real numbers, negative infinity to positive infinity. How about the range? 5 to positive infinity. Is there a bracket or a parentheses on that 5? Bracket. Good. How about increasing and decreasing? Where's it decreasing? Negative infinity up to 4 with a parentheses on 4, and then increasing from 4 to positive infinity with a parentheses on 4. Everybody good? Yep. Okay, so then the next question, which it says 2 but it should be 5, is not in standard form, okay? So remember I gave you 2 options when we were doing this. One is force it into standard form using complete the square. And the other is negative b over 2a to get your x coordinate of your vertex and take it, plug it back in to get the y. So you will be asked to do complete the square on your test, which is actually a week from tomorrow, okay? It's only going to cover 3 sections. That's the good news. So we've already done 1. We're going to do 2 between today and tomorrow. We're going to do 3 between Friday and Monday. You'll review Tuesday, Wednesday, and you'll get your test Thursday. So the quiz for this chapter, I'm still working on it, but it will probably be like a take-home video kind of a thing where you'll get a random problem and then you'll be asked to work it out on a video. Right now I'm going back and forth between complete the square and the one we're going to do next. So I'll let you know before you leave here on Friday. We'll not only have gone over what it will cover, but you'll kind of do a practice route so that you can be comfortable. But it will probably happen over the weekend, okay? All right, so vertex, if I want to find it in standard form, the first way I'm going to do it is complete the square. So I would say that these 2 get grouped together. This time there's something in front of the x squared term. So before I can complete that square, I got to take that out. So I would take out a 4, and I'd get x squared minus x, leave the space, plus 21. Then I take what's in front of that x term, and I ignore the sign because I'm going to square it, so it eventually becomes positive either way. I'm going to divide that 1 by 2. I get a half, and square it, I get a 4th, and that's what I'm going to add inside the parentheses. And normally I would subtract it from the 21. So whatever you add inside, you would subtract from the outside. But because we have taken out something this time, I have to multiply that number times what I'm combining with the one on the outside before I can combine it. So what's 4 times negative 1/4? Negative 1. So now I'm really doing 21 minus 1. So 4 times x squared minus x plus 1/4 plus 20. And then my last step is to just put that into one expression that is squared. So I am factoring it. I've forced it in to become a perfect square trinomial, and now I want to factor it. Square root the first term, square root the last term, take the sign from the middle, put it in parentheses and square it. And now my equation's in standard form, and I should quickly be able to get the vertex out of it, which would be what? 1/2 and 20. Good. Questions on that method? Russell? All right, so I'm going to kind of quickly go through the other method to doing this, which is negative b over 2a. So the first method is complete the square. The second method is finding the x-coordinate of your vertex by doing negative b over 2a and then plugging it back in. So from my original equation, my b is negative 4, the opposite of negative 4, over 2 times a, which is 4. And I get 4 over 8, which is 1/2. That's the x-coordinate of my vertex, and it matches what we already found, which makes sense. To find the y-coordinate, I just take that and plug it back into the original equation. So y would equal 4 times 1/2 squared minus 4 times 1/2 plus 21. 4 times 1/4 minus 2 plus 21. This is 1 minus 2 plus 21. Negative 1 plus 21, which is 20, and that's the y-coordinate of my vertex. And again, they should match. So 2 ways to do it, both give you the same answer. And you need to know how to do both because you're going to be forced to do complete the square by itself, and then sometimes it's easier to do negative b over 2a. You're going to want to know how to do that one when you're graphing. Questions on any of that stuff? Okay. All right, chapter 2, section 2 is called Polynomial Functions of Higher Degree. So instead of just graphing like an x squared or an x to the third, now we can be graphing stuff like x to the 5th and x to the 7th, okay? Just like before, we kind of baby step our way in with the easier, more simpler graphs, and then eventually you're going to start to find your zeros. You're going to start to see these graphs go up and down kind of a thing. And again, some of them you'll do without a graphing calculator where it's like factorable and you can find your zeros. And then some of them you'll need your graphing calculator for. Probably not today, but for tomorrow. So what are these graphs? These are continuous graphs. Polynomial functions of degree 2 or higher, so x squared or higher, have graphs that are smooth and continuous, which means there's only rounded curves, no sharp corners. So these are not absolute value graphs, right? These are round, raised to a power. And there's no breaks drawn without lifting your pencil from a rectangular coordinate system. So if I start to graph, if I go start from finish, I never have to pick my pencil up, okay? This is not piecewise. There's not going to be any breaks in your function. It's going to go fluid from one side to the other. So these are just examples of what they should look like and what they shouldn't look like, okay? Top left, it would be these are graphs of actual polynomial functions, okay? They're smooth and they're rounded. There's no breaks, okay? Bottom right, now you're looking at ones that would be not polynomial functions, okay? So the bottom left, like where it's a piecewise function where there's a hole, it's discontinued, right? There's a break in that graph. That would not be a polynomial function, or if there's a sharp corner. So if you find yourself graphing something like this, obviously you're doing something wrong, okay? You want them to be nice, rounded, with no breaks. So we start with a monomial function. What's a monomial? Mono means one. This is a single term that is raised to a power. So you'll see something like x to the third or x to the 10th, okay? One term. If the n, which is the exponent on that variable, is even, your graph is going to resemble the graph of a quadratic function or a parabola. If the n, which again is the exponent on that variable, is odd, then your graph is going to resemble the graph of the cubic function. So this is going to look something like this. And this would look something like this. So even looks like a parabola, odd looks like the cubic function. And the greater the value of n, so the higher the exponent, the flatter the graph is near the origin. I'll let you write it down and then I'll kind of give you an example of what that looks like. All right, so let's think about what's happening here, right? So let's say I have a graph, right? Let's say I have a graph that is just f of x equals x squared, okay? So I've got a 0, 0, I've got a 1, 1, I've got a negative 1, 1. That won't change if it's squared or if it's raised to the 4th or it's raised to the 6th, right? Like x to the 10th, if I plug in a 1, what is 1 to the 10th? Still 1, right? So those points are not going to change. What will happen outside of that obviously will change. It will increase faster. But what's happening in between is what we're talking about here, okay? So if I were to actually take and plug in, let's say I'm going to plug in one of the, a decimal in between 0 and 1, okay? So let's say I plug in 0.1. What is 0.1 times 0.1? Or 0.1 squared? 0.01, okay? So it would be a point like here, right? And it would keep going up and increasing, let's just say like that. Now compare this to the graph of f of x equals x to the 6th, let's say. 0, 0 is still going to be there. 1, 1 is still going to be there. But what happens when I do 0.1 to the 6th? What is 0.1 times 0.1 times 0.1 times 0.1 times 0.1? What happens every time I add in one of those exponents? Another 0. So this is 1, 2, 3, 4, 5, 6, 1. Okay? So while you can't really read that on your graph, and I'm not expecting it to be 100% accurate, what you need to do is understand the difference between these graphs. The higher the exponent, the flatter this is before it hits that 1. And then the faster it increases after it hits that 1.
Flat is wider.
Flat is like wider, but not past the 1. That's where it's happening. So it's really happening just between the vertex and the next whole number. Does that make sense? It flattens out there, so it kind of like bottoms out, but it's never actually horizontal because it's always increasing. So while it looks like it's kind of flattened out there, I didn't do the best drawing there. It's never actually horizontal, right? Because every time I raise it to a power, it gets a little bit bigger. It's always increasing, okay? But the difference is that the change happens, it's smaller of a change the higher the exponent, okay? So you don't need it to be exact. I'm not expecting you to graph these exact, like you're not going to actually plot those points in between. But what you should be able to do is compare two graphs. If I give you a graph of an x squared and I give you an x to the 6th, you should be able to tell the difference. And the difference is that around that origin or around the vertex, the x to the 6th is going to be a little bit flatter. Does that make sense? Yes? Same thing for the cubic function. So if I look at this as the cubic function now, if it said x to the 3rd, I'd still have a 0, 0. I'd have a 1, 1, a negative 1, 1. And then in between here, my function would look something like that. 0.1 cubed would be 0.001. But if I now say that this is, let's say, to the 7th, okay, it's going to flatten out around the origin. And then it's going to increase at a faster rate outside as we get past the 1, okay? Because instead of just raising it to the 3rd power, we're now raising it to the 7th power. So again, around the origin, The higher the exponent, the flatter that line's going to look. Does that make sense? So you just want to be able to compare them. Again, this is not an exact science. All right, so sketch your graphs. Use your transformations and what the graph should look like, what that parent function should look like, to sketch these graphs. All right, so an x to the 7th resembles what graph? The cubic function plus 1 does what? Up 1. So I'm going up 1, and it's going to be a little bit flatter around that point, okay? Again, these are transformations which are just approximations. Those are not exact points. How about x to the 4th resembles what? A parabola. The minus 1 on the inside does what? Shifts it to the right one. So I'm going to the right one. It's a parabola, and it's a little bit flatter at the bottom than my normal parabola. Okay. Questions on either of those? So those are only for monomials. Then we're going to start to learn what to do with all the other terms. All right, so this is, I think this is funny. Like, this is how your book describes it, right? Like, you have to decipher what all that means, okay? And the next slide, I try to put it into plain English. But this is called the leading coefficient test, okay? The leading coefficient test determines the end behavior of the polynomial functions. End behavior is what is happening to the left arrow and what is happening to the right arrow. Okay, meaning is it pointing up or pointing down? Is it rising or is it falling? So if you are looking at your function, and this whole thing just means a function in which there are exponents involved, okay? Then to do the leading coefficient test, we are looking at the highest exponent. Sometimes it's first and sometimes it's not. So you got to find the highest exponent. And if the exponent on that degree or on that term is odd, then one of my arrows is pointing up and one of them is pointing down. Think about the cubic function, right? One goes up and one goes down. So if the highest exponent, so I'm doing this, if the highest exponent is odd, one goes up, one goes down. And then to figure out which one is which, I look at the term on the front of that variable. If that term is positive, then it rises to the right and falls to the left. If it's odd but negative, it rises to the left but falls to the right. As this section goes on, we're going to start to figure out what happens in between those two arrows. But for right now, all you're looking at is the end behavior. If the highest exponent is even, then it resembles a parabola, which means both are going to go up or both are going to go down. If the number on the front of that highest exponent is positive, then both point up. And if they're both negative, if it's negative, then they both point down. So we are first just determining what the arrows look like at the beginning and the end. And then we're going to find the zeros and the turning points and all that stuff in between. So that's what this says, okay? An odd degree polynomial, so degree is the highest exponent. An odd degree polynomial has opposite behavior at each end. If the a is positive, the graph falls left and rises right. If the a is negative, then the graph rises left and falls right. An even degree polynomial has the same behavior at each end. If a is positive, then both ends point up. And if a is negative, both ends point down. All right, so it just says use the leading coefficient test to determine the end behavior of the graph of f of x equals negative 3x to the third minus 4x plus 7. So the first thing you do is identify which is the one with the highest exponent, and sometimes it's first and sometimes it's not, okay? What's the highest exponent on this function? 3, right? Or cubed, which tells me what? Without even looking at the number at the front. If it's odd, then what? Are they both going in the same direction or one going up, one going down? One goes up, one goes down. To figure out which one does what, I look at the coefficient on the front. So the coefficient of the x to the third term is what? Negative 3. If it's negative, that tells me what? It rises left and falls right.